Hello everyone. So now that we have understood the Dirac notation in quantum mechanics, here we will discuss about perturbation theory. So I'll give a very quick intuitive understanding of what perturbation theory is, and then we will move to the perturbation theory in quantum mechanics, the time independent and the time dependent part. So consider classical mechanics. Okay. So let's try to understand perturbation in the context of classical mechanics. So basically in classical mechanics, consider a harmonic oscillator. So what's the whole idea of harmonic oscillator is that it moves under a potential which looks like this, which is a function of the location half kx square. This is a well known fact. And what is the differential equation that it follows? That follows this differential equation, m d square x dt square plus kx is equals to 0. Okay. Now the idea is the following: is it possible that we change this potential under which the harmonic oscillator is moving very slightly? So change is small. So let's do a small change. So instead of V0, let's take some potential V prime x, which is the new potential under which the harmonic oscillator is going to move, and let it look like this. Let the old potential be as it is, and just we add a very small term epsilon x cube. Now the epsilon is so small that it almost tends to 0, for example. Okay. Now so you are giving a external perturbation which is very small. So what do you expect in such kind of cases? In such kind of cases you expect that the behavior or the motion of harmonic oscillator will not deviate too much, but there will be a little bit deviation. What do I mean by a little bit deviation? So in this case, how is the motion of harmonic oscillator, how x varies with time? Usually we have a sine omega t. Okay, this is the solution of the differential equation. Let me call this solution as x0 t. Then in such a case, the motion or the solution will actually be the original solution, the unperturbed solution, and because of the introduction of this perturbation, definitely the way it will move will a little bit be different. So to first order we have epsilon x, say 1 of t. Okay, 1 of t is some different function that gets added to the original case. So this is what happens when you add small perturbation. So basically small perturbation means that the new motion of the system will not deviate too much, but there will be a slight deviation from the original motion. That's the whole idea of perturbation. Okay, let's try to understand it in a different context. How about let's talk about matrices. So in matrices we can also use this whole idea of matrix eigenvalues and eigenstates to depict what perturbation actually mean. So consider a matrix A. The matrix looks like this: 3 0 0 2. So this is a diagonal matrix, so it is quite clear that it has two eigenvalues. One eigenvalue is 3, another eigenvalue is 2. And basically what will be the eigenstates? So the first eigenstate will look like 1 0, and the second eigenstate will look like 0 1. So you can easily find the eigenvalues and eigenstate of this matrix. Okay, this is quite clear. Now the idea is something different. How about I change the matrix but only very slightly? So change is small. So change is small. So I change the matrix only very slightly. Okay. So how do I change the matrix? So I take the original matrix as it is. So the new matrix is original matrix as it is, and then what I do is I add another small matrix which looks like this: 0 epsilon epsilon 0, and then epsilon is very small, epsilon is very small, tends to 0. Now why I am doing this, what I am trying to claim is the following: given this new matrix, which is a sum of the old matrix plus some extra perturbation added to it, which looks like epsilon some matrix B, where I can define B as 0 1 1 0. Okay, so now my question is, what do I expect with respect to the eigenvalues? What will be the new eigenvalues? So my guess is that since the change is very small, so I guess that the eigenvalues will be nothing but the old eigenvalues of the original matrix, plus there will be some, some extra term, some small extra term. Similarly, my guess is the new eigenvalue, the second one, will be the old eigenvalue plus some extra term, and this extra term will be very small. Okay. Now this is a big claim. We have not proved it yet. I am just saying that maybe this is possible. Now my idea is I have to prove that this is indeed true when you add matrices of such nature such that epsilon is very small. So I need to prove it. So how do I prove it? So the best way to prove it is I take the new matrix, which is A prime, which is equals to 3 epsilon and epsilon 2, and I actually calculate its eigenvalue. That's the best I can do. So how does eigenvalue is calculated? So you take the matrix, you take a state, and the idea is you get the state back with some eigenvalue. So this is the eigenstate, you get the eigenstate back with some eigenvalue. So that means that if the state is non-zero, then this matrix, so A minus say lambda I, or A prime minus lambda I prime, okay, is singular, is singular. Why? Because as you can easily see that this thing can be written in different forms. I can write it as A prime minus lambda prime I, and then I can have the state V here, which is equal to 0, and then for all these things to be for this particular object here to be singular, the determinant should be 0. So this is the normal known fact about finding eigenvalues and eigenstates. So let's find the eigenvalues. So since the determinant has to be 0, so let's do the calculation. So the determinant of the matrix A prime minus lambda I, which will look like this: 3 minus lambda epsilon epsilon and 2 minus lambda must be 0. Let me draw a straight line here. That implies, what do we get? We get 3 minus lambda and 2 minus lambda minus epsilon square is equals to 0. And then what are the values of lambda? So lambda will look like 5 plus minus root over of 1 plus 4e square divided by 2. Now you would argue that these values of lambda, basically these are nothing but lambda prime, so I should write prime here. So you get two values of lambda prime depending on this is plus or minus. Now you'd argue that, hey, the lambda prime does not look like old lambda plus some extra term, doesn't look like this at all. But my claim is it actually does. But then you have to understand a very interesting fact. Since we are claiming that epsilon is very small, that means that any object which looks like this can be approximately written in this form. It's very simple. So basically this particular term can be further simplified, and this simplification is allowed because epsilon is small, and this is the most important part where you understand that how perturbation work. So what happens to the lambda prime? It looks like 5. So one value will be 5. Let's write it generally. It will be like this: 1 plus 2 epsilon square divided by 2. So what are the two values? So one will be on the minus side. So let us take it as lambda 1. Let's use plus. So if you use plus, you get 3 plus epsilon square, and if you use the minus sign, you get 2 minus epsilon square. Quite interesting, right? If you look at them, these are of form that the new eigenvalue is the old eigenvalue plus some term, and again the new eigenvalue is the old eigenvalue plus some term. So basically we were able to prove, note this, we were able to prove that what we argued in the beginning, that if you add a small perturbation to the matrix, then the new eigenvalues will be old eigenvalues plus some extra term, and it is actually true, and this thing is getting true because of this idea here. Since epsilon is small, you can use this argument, and you are allowed to use this argument because epsilon is small. That's the whole point. That's why in perturbation, whenever you use any extra terms which are added to the original Hamiltonian, these terms are very small in nature. So since they are very small in nature, you can use these kind of approximations as you can see here, and then you can say that okay, the new values because of the perturbation will be old values plus some extra term which will be small in nature. And this is fundamentally the whole idea behind perturbation. We saw it in two different ways. We saw it classically, we saw it in matrix form, and what we did in matrix form is going to help us understand quantum mechanically, because when we will do time independent perturbation theory, our Hamiltonian will be 2 cross 2 matrix which will look like this. We will add perturbations, and then we will see what will be the first order corrections and second order corrections to wave function and energy. So basically here when I say some small term, so these are corrections term. Why we call them correction? We say that okay, since you have added a new small term, so the new values will be some term plus the original value, and these term that we add, we just call them corrections. This is just a uh, terminology alert, you get corrections. Okay, so don't be confused with these words, but the fundamental idea is clear, that the solutions of the actual solutions will be the old solutions plus some extra term. And let's look at the same perturbation theory from quantum mechanical point of view in the next lecture.